Welcome back. Thanks for making it up to the last lecture. So finally today I'm going to speak about spin glasses, the thing I had been advertising in the first lecture. So it did come after all. So I'm not going to try to go over motivations again. I think I already gave you some in the first lecture. So I'm going to try to directly go into discussing what these models are, how they are defined precisely, and write down the free energy, and again focus on this problem that has been my, like the center of my attention during the whole series, which is how do we compute it? So as you already have been told, for spin glasses, results are less definitive than for the models we have seen so far. So be prepared for partial results. So the most basic model of a spin glass, for which actually we do know, since without using PDEs, what the limit for energy is the SK model. Let me remind you how this is defined. So let me say that let's set this. So for every sigma in Rn, let us set Hn of sigma to be 1 over square root of n, sum of wij, sigma I, sigma j. Okay, sum over all I and j between 1 and n, where the wij's are independent standard Gaussians. Okay, so I set it up in Rn because a bit like in statistical inference, you can define the function everywhere, and then in a later step, when you write down your free energy, you can have this measure, this measure on the probability measure on Rn, which is going to specify for you exactly, how you kind of restrict this sigma, for instance, to be +1 -1. And it's true that it's going to simplify our lives to, in particular, consider this case. So oftentimes, when I'm going to talk about the SK model, I'm going to assume that the measure Pn, that in general is just some probability measure on Rn, is actually of product form, and moreover with P1 being supported on +1 -1. Okay, but I'm going to often try to write things down in a way which would be less sensitive to changes of the measure Pn, so that you have also a sense of what you could do in case your spins are not +1 -1. Okay. Okay, so this will be one model that we are going to try to carry along as we discuss spin glasses. As you know already, I've been also interested in another model which we could call the bipartite model, where these spins or these indices are organized over 2 layers over a bipartite graph. So let me write this bipartite model. Perhaps before I move to this, we had also calculated the covariance function, I think, for this object. Okay, so let me write it down one more time. For every sigma and tau in Rn, if you so this Hn of sigma is a centered Gaussian. It's a centered Gaussian field if you think about it as a function defined over all of these possible sigmas. And so it's going to be interesting to look at the covariance of this Gaussian field. And that covariance, I think we had done the calculation, but in any case, it's not a difficult calculation. Maybe I had just said it in words, but it's really a simple calculation to play with these independent Gaussians. What you get when you calculate the covariance is you get the square of the scalar product between sigma and tau. Okay? So equivalently to giving you the explicit formula, I could have told you define Hn of sigma to be the unique centered Gaussian field whose covariance is given by that. Okay, and oftentimes this is actually a good point of view to take, at least from the point of view of what we're going to want to do. the main advantage of giving the explicit formula is that, well, it's kind of obvious that this thing exists. While if I tell you, take the covariance like this, not every function here is going to be a valid covariance. So you have to wonder whether the field exists. So we know it exists because here it is. Okay. So for the bipartite model, we think of the sigma as being split into two parts, sigma 1, sigma 2. Each of the parts, I think of it as a vector in Rn. And again, I'm going to just set that the two vectors are of the same length, but you could also imagine that they have different lengths which are proportional to one another, multiples of n. Okay. That will also be fine. And Hn of sigma in this case, maybe I'm going to use the same notation, but I'm going to indicate each time this is the SK model, this is the bipartite model. Okay. And if you're ever not sure which model I'm talking about, of course you can ask. And hopefully, we're going to avoid confusions. Okay, and this is how it's defined. So if I was doing a graph, you would have your units like this, and then the other units, okay, so I said it's the same size. And then they only have interactions across the layers like so. Okay, I don't draw all the links, but you see the idea. Okay, there are no connections within the layer, but there are connections across the layers. You have this bipartite graph, while here it was more like the complete graph that was underlying the interaction structure. All right, that's the definition. And again, most of the time, maybe let's say all the time, I'm going to focus on the case when the reference measure that we take is such that each of the coordinates here is +1, -1. Just again, because it slightly simplifies certain aspects, but yeah, I'm going to still try to gesture at how to deal with marginal measures as we proceed, so I'd like to keep this notation. And also to clarify that you don't need to restrict your attention to situations when these two layers have this symmetry. Like here, I set them to be of the same size. So just to make sure I can break the symmetry, maybe I'm going to allow that each of, the way this is distributed is not necessarily the same as this one. Okay, so maybe there's each of them is IID on the set +1, -1, but maybe one has a bias that is different from the bias of this one. Okay, just to make sure that we don't have the symmetry between the layers. Okay, Okay, so this is the setup. Again, we can calculate the covariance. And what we find this time is that in some sense this square splits into scalar product of sigma 1 with tau 1 and scalar product of sigma 2 with tau 2. So far, so good. So I like to talk about the bipartite model very much because, first of all, I think it's motivated by a number of things. And also, it's a good representative of a class of models that we don't understand. So instead of always trying to speak in the greatest generality possible, I just like to specify this one and say, here is an example I don't know how to solve. But just so that you have an idea, let me also write the more general situation, which at least as far as I can see so far is essentially as difficult as this one. I don't see any significant difference. So let me also write the general model. okay, sometimes there are a couple of small difficulties, but okay. In any case, this is the general model is the model that we actually use when we write a paper, for instance. Okay, so the first paper maybe was just on the bipartite, but since then we just write things in some more generality. So what would we want to write down for a more general model? Well, maybe instead of two sorts of spins, we could allow a finite number of them, not just two. So let's say we would fix a number. I think I'm going to call it capital D. So let's say sigma now is going to be sigma 1 up to sigma D. And if I want to be a bit fancy, I can let them be in somewhat arbitrary Hilbert spaces, but think of it as being Rn. Okay, so think of this as being Rn, but it could be some other Hilbert space. And then we said that Hn of sigma indexed by this thing, is a centered Gaussian field with a specific covariance which only depends on the matrix of scalar products between these guys. So is a centered Gaussian field. With covariance given by, so let's say for every sigma and tau in this Hn D, I'm going to specify that the covariance between Hn of sigma and Hn of tau is n times some function of the matrix of scalar products. So sigma D dot tau D prime divided by n, where D and D prime range in from 1 to capital D.
Do you have like an example of relevant model where the underlying Hilbert space is infinite dimensional?
Yes. So hopefully I'm going to. Well, in practice, I kind of like to try to approximate it by a finite dimensional one, but we're going to see as we do the enrichment. Hopefully, I'm going to explain a little bit how you do it. And it's convenient to think of it as being embedded in some Hilbert space, which is a bit different. That's why I set it up like this. But okay, just let's just say it's Rn for now. It's okay. There's no. Yep. And where xi is some smooth function, let's say. Very nice, well-defined everywhere. Okay, and then it's a okay. It's some question you can think about. Which functions psi are such that this is a valid covariance function. Okay, it's not a very difficult question to resolve, and perhaps I'm not going to say too much about this, but okay, at least you have examples on the left. Okay. Perhaps one example I'm going to mention later, which people call p-spin. In the case d equals 1, just a single type. For instance, what you can do is you can put any power here. If you put a p here, which is an integer, a non-negative integer, then this is a valid covariance function. And the way to observe this is, for instance, if you want p equals 3, what you do is you write a sum over 3 indices of w I, j, k, sigma I, sigma j, sigma k. Okay, and then you see how you generalize to other integers. Once you have managed to create an example with a specific covariance function, and then another one, you can also add them together by choosing your new Hn to be a sum of the independent copies of the guys. So these are the basic operations you can do. All right. And if I keep with this general model, perhaps I'm going to write here. Maybe I'm going to erase the definition of Sk beforehand. So in this general setup, we're going to also give ourselves a priority measure. And yeah, when we do even the general model, we still assume it's a n-fold tensor product in the sense that you know, just like this one is an n-fold tensor product. I'm not sure how to write it down very nicely, but I mean that sigma 1i up to sigma di, as you vary the I, they are independent coordinates. This is the setup in which it's most convenient to work. Okay, so maybe I put between quotes because when I write it like this, it's not really consistent with the notation I was using here, but because the indices are a little bit mixed up. And the free energy in this general setup is going to look like this. Maybe I'm going to write it here. So you want to take the log, okay, divide by n as usual, and then the integral exponential of some parameter, and as you know now, I like to put square roots in front of things that are Gaussian. So square root of 2t, hn of sigma. And then it's going to be pleasant for me to make this be like if you're writing this exponential martingale thing. So this is a Gaussian. You know, think of it as being a sort of Brownian motion as t varies, and then I'm subtracting half of the quadratic variation. So this is t times the expectation of the square of hn of sigma, which I can replace by its expression here. So it's t times n of psi of sigma d dot sigma d prime over n. d prime. dpn of sigma. Okay, so this is the free energy that is analytically. So this extra term here is analytically convenient when we do calculations. That's why I introduce it, even though perhaps right now it looks like not really something we wanted to have around. A posteriori, you can try to think about how to remove it. What is nice with this guy is that it's no longer a random term. You know, the random part is here. This is a random quantity. This is not a random quantity. So you have to do something to take it out, but it's less demanding than dealing with this part. So I make my life as easy as possible to study this part, and then we deal with whatever we have done later. Okay, and the reason that I like to specify these simple measures in the SK case, which I erased, and in this one with the support in +1, -1, because in this case, this term, it's clear that we can deal with it because it's constant. So then we can deal with that. Let's verify this. So yeah, so maybe I can look at it here. So it's the variance of hn of sigma. So when sigma equals tau, and sigma, if you have these guys being supported on +1, -1, in particular, sigma 1 lives on the sphere, and so you're calculating the norm of sigma 1 squared. This is going to be n. Okay, and this is n also. So for SK or bipartite, with the choice of Pn I described, this term will be just t times n. Okay? So then I don't need to gesticulate to tell you that we can deal with it. It's just a constant. Sounds good? So since I built in the definition of the free energy, I did this compensation part. You see that, in particular, if I were to take the expectation of this exponential, it would give me 1, right? So if I take the expectation outside, by Jensen inequality, it's going to give me something which is smaller, so it's going to be negative. And I prefer positive things, so I'm going to put a minus sign. Okay. So now be careful. My free energy has the sign convention is changed compared with what we had been doing so far. Okay, so physicists would be happy. They prefer the sign convention like this with the free energy. And yeah, so oftentimes we are going to also take the expectation. Perhaps because I'm not going to be ultra precise today, I'm going to just define the average free energy, which then is exactly what is written here. Okay, so this is going to be Fn bar. Maybe I still don't have enough parameters. Okay, so maybe with a circle to keep the notation as in statistical inference. Okay, because we have still only one parameter here. Okay. So, yeah, like in statistical inference, we are facing this problem with the T, and we're hoping to calculate the free energy. And we have, for inspiration, we have what we have done for Curie bias and for the statistical inference. And in both cases, the idea was first to add a term with which to play with, so that we would find relationships between the derivatives of the free energy. And we have to add a term which is not too complicated, so that we are not making our life even more complicated than the thing we're trying to do in the first place. So yeah, we have to think about what things we can do, what terms we could add to this energy function to help us to calculate the limit free energy. And perhaps one first guess one could have to, when we think about this, let's say in the SK model. So we are trying to find a simpler system which in one way or another looks like the spin glass case. And I'm going to write something a little bit trivial perhaps, but the energy function for SK, I could rewrite it like this. You know, I first sum over A, and then I regroup the terms over J, and then I write it like this. Okay, and because we want to add something simpler, it would be nice if what we add is something that has no interaction between sigma I and sigma j. So perhaps, you know, we see this, which looks kind of random, so perhaps we could try to see what happens if inside the energy function we add something which looks like a sum over I of, I don't know, some random thing, maybe some Gaussian, multiplied by sigma I. Okay, and if you saw the talk of Tim yesterday, or if you check exercise 6.5 in the lecture notes, you will also find somewhat better arguments for just, you know, for suggesting that this maybe looks like a Gaussian in some reasonable sense. Okay, so what we're going to add to the energy function is exactly this thing. So we're going to take independent Gaussians and we're going to add sum over I of Zi sigma I. Okay, and I don't claim this is I have a good justification at the moment for doing this, but we're just going to try and see what happens. Okay, we add this and we see if we find interesting things as we take derivatives. Okay? So the new version of the free energy is going to be like so. So T and H minus 1 over n, expectation log of integral exponential square root of 2t hn of sigma minus nt. So I'm just writing it for SK bipartite. Okay, we have this simplification for this compensation term. And then I add also my new part, square root of 2h z dot sigma, okay, where z is a Gaussian vector. And you know, I like to do these compensation things, so I keep doing them. I subtract minus n times h, dpn of sigma. Okay, where z, okay, so maybe I should have said earlier, so t and h are non-negative, and z is a standard Gaussian vector. Let's say n-dimensional Gaussian. All good? Does the definition make sense so far? So we want to calculate this. And as we're used to now, we can introduce notation to speak about the Gibbs measure with respect to this energy function. I'm going to write it with the bracket as usual. So now when I write bracket of g of sigma for some reasonable function g, I mean the integral of g of sigma exponential of that thing above. Okay, everything that is inside the exponential divided by the normalization part. Looks reasonable? Yes. So, like with statistical inference, we can do this derivative calculation. For instance, if we differentiate with respect to h, we're going to find 1 over square root of 2h, z dot sigma, maybe minus n. And now we are used to seeing this 1 over square root of 2h times Gaussian times something. So we do our integration by parts trick again, and we find a relatively nice expression as a result. And the compensating term here is made so that we find an expression which is as nice as possible. Okay, so if we do this calculation, let's say Gaussian integration by parts. Integration by parts. We find that when I differentiate with respect to h, I get the expectation of this scalar product between two independent copies of this random variable sigma. So I should have said that sigma is an independent copy of sigma under the bracket measure, under the Gibbs measure. Okay, a physicist would call it a replica. So I hope it evokes the statistical inference situation. And when we differentiate with respect to t, what we find instead is going to relate to the covariance function of this Gaussian field. This is what's going to be important when you do your Gaussian integration by parts. You will find like a general statement with this Gaussian integration by parts nicely encoded in the notes. Here I'm just going to splash you the result, but again, not very difficult to justify. Just you take your time to do the integration by parts carefully. And what you find is that in this case, the t derivative for the SK model, so this is for the SK model. Everything that I wrote here is for the SK model, I should have said. It seems that for the SK model, we find we are in our very well-known terrain now. We like in Curie bias or like in statistical inference, it seems that the t derivative wants to be like the square of the h derivative, and the difference is some variance term. So dt f n bar minus d h f n bar squared equals, so let me write variance, even though there are two levels of disorder again. But okay, it's just a bit shorthand to, maybe I indicate that it's variance with respect to both probability measures that are around of this. I'm going to call this the overlap, like the scalar product between the two copies, these two replicas. We can call it the overlap between sigma and sigma prime. So we are there. And it looks pretty good. We've been used to seeing these things show up. And so far, we've been managing to work through the statement that in the limit of large n, this Fn bar is going to converge to the solution to the PD that you're thinking about. And the steps were to try to express this in terms of Fn bar itself. Okay, but now we no longer have our nice Nishimori identity at hand. If we start to calculate higher derivatives of the free energy, it's going to be difficult to relate them to this term exactly. You will have even more replicas, more of these copies of sigma showing up in your calculation, and there is no obvious relationship with that term. And if you kind of listen to physicist wisdom, they will tell you that for small t, indeed, this variance will be small. But as t gets large, this variance will no longer be small, and so your hope to show that in the limit of large n, the equation blah 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 will be satisfied are just too optimistic. Okay, and it's not just that the variance will not be small at some specific points. It's just not going to be small everywhere, like, period. Okay, so variance is only small for small t. Is, however, okay, so physicists in this case say that there is replica symmetry breaking. Perhaps I should take 1 second to explain the terminology. Perhaps I could first try to explain when it is that physicists would say there is symmetry breaking. When there is a symmetry in a problem, in some sense the symmetry will be preserved, and still physicists sometimes will say there is symmetry breaking. So just to give you an example, if I try to put my chalk at equilibrium vertically like this, I can say, oh, I'm going to manage because by symmetry, there's no way it's going to choose a direction and tilt, right? Because by symmetry, the solution must be that it stays vertical. But maybe I'm not going to try, okay? And you could say that when I drop the chalk, the symmetry is broken because it chooses the direction. But in truth, from a mathematical perspective, it's not really broken. It's just that I cannot predict in advance in which direction it's going to break the symmetry. And so it's just that the set of solutions is becoming symmetric, but the specific solution that is being picked is not symmetric, right? So here, similarly, when they say there is replica symmetry breaking, they mean that these replicas, they are completely exchangeable, right? They are just independent copies of the same thing. So when you look at their scalar products, in other words, when you look at the distance between one and the other, or let's just say their scalar products, because of the symmetry, you should expect that they are all at the same scalar product. Okay? Because you're like, they are the same. So why should one be closer than the other or whatever? But because, in fact, this scalar product is random, if you pick 3 independent copies of sigma, they will possibly be at very different distances from one another. Maybe 2 will be very close and the other will be far away. And so in some sense, the symmetry is broken between the replicas. But of course, from a mathematical perspective, it's still the case that these things are exchangeable. It's just that the scalar product becomes random, even though perhaps from some high-dimensional geometry intuition, you would expect them not to be. Does that make sense? And so this is the problem we need to think about for the SK model. And just to clarify how this would look like for the bipartite model. So in the bipartite model, it's really very similar. The only difference is that you have 2 types of spins. So your first guess should be that you put some external field on sigma 1 and also another one on sigma 2. Okay, just so that you have these 2 moves that are available to you. So there will be H1 and H2 in the free energy. And then, you can guess what I want to write. 1 over n. I forgot the expectation already. Expectation log, integral exponential. Okay, symmetry breaking maybe. Square root of 2t, hn of sigma minus nt plus square root of 2h1 z1 dot sigma. So I give myself now 2 Gaussian vectors minus nh1 plus square root of 2h2 z2 dot sigma minus nh2. Bam, dpn of sigma. Okay, and how does it change then? Well, when you differentiate with respect to h1, you'll find the scalar product between sigma 1 and sigma 1 prime. And h2 sigma 2 prime. And when you differentiate in t, you will find instead of the square, the product of these scalar products. So let me write this. So dt fn bar equals expectation of sigma 1 dot sigma 1 prime over n, sigma 2 dot sigma 2 prime over n. Yes?
Are you just taking this scalar product there with sigma 1 and sigma 2 respectively, or with
Oh, say again? Did I?
Z?
Oh yeah, thanks a lot. Yeah, exactly. Yeah, thanks a lot. I had missed that. Thanks a lot. Are there other mistakes I have made or corrections to do? Good? Or questions? Okay, and maybe I'm not gonna write, but you see what the derivative with respect to h1 will be, and with respect to h2. So dt fn bar minus the product of the derivatives. I could write it as the expectation of sigma 1 dot sigma 1 prime over n minus its mean value multiplied by the same thing with sigma 2. Okay, I'm kind of squeezing it in the corner here, but I hope you can read it. Maybe there's another bracket I need to close. Okay? So in particular, in this case, like in earlier situations, you can, if you assume for a second that these things don't fluctuate much, then you can control the size of this left-hand side. Just because you can say fn bar that xy is smaller than 1/2 of x squared plus 1/2 of y squared, for instance. So this is smaller than, let's say, 1/2 of the sum of the variances. Maybe I'm going to write like this, of sigma a, the sigma a prime. Maybe I should write d to be consistent. Over n, d from 1 to 2.
The classical covariance term. So
Yeah. Okay, so this should evoke like a generalized Curie-Weiss sort of situation. Okay, we can understand the absolute value is small if we know that the variance is small. Okay, and we see if we were facing the most general model with this function psi describing the covariance, what we find when we take the t derivative is the expectation of psi of these scalar products between sigma and sigma prime. And so you would want to say that dtfn bar is like psi of these derivatives with respect to h. Okay, so sometimes psi is convex and sometimes it's not convex. For instance, for bipartite, it's not convex. Okay, so perhaps what I want to do right now is to convince you that indeed for t small, this variance is not going to be small. Okay, so that you have some feeling that indeed there is something to be done. It's not just we are listening to physicists and believe what they say. Say again?
You said for t small, it's not necessarily small.
For t small, it's going to be small. So t small usually is the easy regime. And then but as t grows, we are going to have problems. Because for t small, for t equals 0, for instance, the sigma wants to be uniformly spread around and everything's nice. For t large, the sigma wants to do complicated things that are more difficult to describe. So, yes?
Does that have to do with sort of like the geometry of like minimizers of the energy?
Sort of, yes, indeed, yeah. Because in particular, the optimizers of the energy function, they really relate to very large t things. And indeed, the structure of the near optimizers is going to be not very simple. It's not going to be just.
They will have a lot of intersections.
they will have a structure which is going to be very rich, and which I'm going to try to describe progressively. Like I'm going to progressively build up towards this. Maybe I'm going to see what I can do here. So in order to convince you that there is something to be done, that indeed this variance is not going to necessarily be small, I'm going to discuss for a moment a toy model, which is not really among the class we have seen. And you can think of it as, so it's going to be only with one type, like with the sigma scalar tau to the power of 2. You can think of it as the version with the power of p, but where I send p to infinity in some sense. So if you imagine p is extremely large, sigma scalar tau over n to the power of p, and your sigma and tau live on the sphere, then, well, either they are equal, in which case this is 1, or they are not equal, in which case this is basically 0. Okay, so my toy model is, let's just pretend that we have independent energy functions. Okay, does that make sense? Okay, so let's say toy model is called the random energy model. Maybe I'm not going to write it in full. Random energy model is you decide that Hn of sigma are independent. So perhaps I'm going to set it up like this. So I'm going to give myself independent standard Gaussians. And this time I revert to indexing it by +1 - 1 to the power of n, because otherwise this is crazy. So these I take as standard Gaussians, but in truth our energy functions, they have variance n. Okay, so I'm thinking that the true energy is square root of n times this guy. Okay, so I would like to understand what's going on with exponential of the square root of 2tn times E sigma. Okay, I think of it as being the probability measure that I care about wants to put a weight proportional to that number to the configuration sigma. Does that make sense? Okay, so let me see how I want to explain this. So in particular, if I want to focus on the behavior of the maximum, like the configuration sigma that has the highest probability weight, this probability is going to be described by the max over sigma of that thing divided by the sum. Okay? And so this is a sort of question that should evoke to you how do extrema of independent random variables behave as we take many of them and we try to rescale things in some way or another. Okay? So if you don't know these sort of results in advance, I really strongly encourage you to think about them, because as far as I'm concerned, I consider them to be of similar importance to the central limit theorem. I think it's very important to know how, when you take IID random variables, let's say you take n of them, and you look at the behavior of the maximum, you have to, it's kind of important knowledge for scientists, let's say, to understand how this behaves as n goes to infinity. And there is a dedicated section in the book which we try to make self-contained, so I think it's section 5.4. So if you're not aware of this, I really strongly encourage you to have a look at it. But I'm going to also describe a little bit the results here. So here it's not exactly the standard situation when we study maxima of IID random variables, because I do two things at the same time. One part is like the classical case, I take more and more random variables, but at the same time I also change them as n varies, because I take these guys and I multiply by square root of n, I take the exponential. So as I change the n, even the random variable itself is varying. but we'll say that in some sense they still, the same sort of techniques as in the classical case can be applied, and you can understand the behavior of these guys very well. So let me try to describe this. So first I'm going to state it in some easier form. So for some constant, which looks roughly like, so I should add, maybe I'm going to introduce a parameter zeta. I'm going to define it. So zeta is going to be very important. I should have defined it before setting the C. So zeta is square root of log 2 over t. Okay? This is a parameter I define right now. So with this source of zeta, and for some constant which looks like this as n goes to infinity, and let's say for A and B like so, what you can think about, for instance, is so here is my Gaussian weight, let's say. Let's call it like this. So I claim that this Cn plays the role of the leading order behavior of the maximum in some sense. So I subtract it to the energy. And now I'm going to say that this looks reasonable as I send n to infinity. Okay, so Cn in some sense captures the behavior of the maximum a little bit. So if I look at this set, and I think about how many points in this set fall into the interval, maybe I'm going to write here, fall into the interval AB, and I just count these points, okay? This converges as n goes to infinity in low to a Poisson random variable whose with mean value given by the integral from a to b of zeta over x to the zeta plus 1 dx. Okay, so this is not very difficult to show. You can really do it as an exercise in the first class of probability. What's nice, and that's what is explained in section 5 of at the beginning of section 5 of the notes, is that in fact you can put this into a nicer framework that allows you to have this in some sense jointly over many of these intervals at the same time, not just one at a time like it's written here. Okay, and the right way to phrase this is to think of this as a point process, and say that the limit point process is the Poisson point process with this being the intensity measure. Okay, so if you know this in advance, it sounds clear. If you don't, then it sounds perhaps too much, but let me write this. So if I look at this point process, 2Tn E sigma minus Cn, and I forgot the exponential. Then this converges in low as n tends to infinity to a Poisson point process with the intensity given by that, zeta over x to the zeta plus 1 dx. Okay, and so why do I say all this? So let's go back to the question that is on the board here, the behavior of the maximum compared with the sum. And let's think that we are essentially in the limit, and so the object we're looking at, you see the minus Cn does not play any role in this question, right? You can put it in the numerator and denominator, it doesn't change anything. So let's imagine what we're seeing, in fact, is this Poisson point process. So what happens is that when zeta is smaller than 1, if you do the integral of x times this measure, let's say from 0 to 1, you get something which is finite. So the total sum of these numbers, as long as they fall between 0 and 1, is going to be finite. And then to the right of 1, you can see also that there is a finite number of them. So when zeta is smaller than 1, that statement that is on the board tells you that, well, I'm going to write it here, that this is going to converge to a non-trivial random variable. Okay, and on the other hand, if zeta is larger than 1, then this is going to converge to 0. Okay, I mean, you have to think about properties of this thing, but again, this is explained in detail in section 5 of the notes. Can you have a question?
So all the results on this table is valid only for theta smaller than 1?
No, this is true. This is true for every zeta, but the fact that this guy is summable near 0, like integrates x near 0, is only true for zeta smaller than 1. Otherwise, the statement is still valid, but you can sort of use it to infer that the maximum is going to be negligible compared with the sum. Okay, so maybe I go a bit too fast, but okay, so just so you know, Poisson point processes are a good way to think about this, but let's take it for granted that you have the following statement, that when you look at this ratio, if zeta is 1 or greater than 1, then this ratio is going to go to 0. So typically, the probability to fall into the configuration that has the maximal energy is going to be 0. But when zeta is smaller than 1, you have a non-trivial probability to fall in the specific configuration that has the highest energy. Okay? So in particular, suppose zeta is smaller than 1, and I pick 2 independent copies out of my Gibbs measure. Then with some probability, I pick twice the configuration that gives me the maximal energy. And so there, the distance between sigma and the copy is 0, like the scalar product, if we think in terms of being embedded in the hypercube, is going to be 1, right? But okay, now I'm going to argue that you also have some chance to not pick the configuration of maximal energy. So sometimes it's going to be actually just another configuration wherever. So scalar product will be 0. Okay, so you see that on this toy example, there is, as soon as zeta is smaller than 1, your scalar product will be sometimes 1, sometimes 0 with some positive probability. Does that make sense? Or? And just to clarify that indeed you also have a chance to fall into the configuration with the second highest energy when zeta is smaller than 1, let me observe that this is, the second highest energy is also captured using this language, like at the exact same scale. So, okay. I'm not sure how to say it best, but this statement tells you that the difference between exponential of the maximal guy and exponential of the second maximal guy is of order 1. So then, indeed, you have a chance to also fall into the second highest. And so at least on this toy example, one can see that this overlap thing will not be concentrated. Sometimes it will be 1, sometimes it will be 0. Does that make sense? Okay, so maybe we take a short break, and using this insight, we are going to try to improve upon our strategy here, which is a little bit failing, well, not just a little bit, which is failing as t grows. Okay, so I'm not sure if I did a great job at this, but I hope I tried to convey the idea that on this toy model, you have this splitting. Maybe I should wait a tiny bit more. I didn't check the time actually, so I don't know how much time I gave you for a break. Yeah, so I tried to convince you that on this toy model, you have at low temperature, when the parameter becomes high, the Gibbs measure will want to split into all these, how to say, let's say that if you're only interested in getting 90% of the Gibbs measure, you can focus on like 15 states basically, and this will carry essentially everything up to this 10% that you drop. And then when you sample someone, is going to pick one of these 15 candidates, and that will be it. Okay, and if 2 samples fall into the same of the 15, they have overlap 1, and otherwise they have overlap 0. Okay, and this was on a simplified model. And surely the true spin glass case cannot be simpler than this, right? So it will allow this sort of behavior to occur. Some models will indeed behave like so. We'll have this splitting into maybe 15 different sort of states that carry most of the Gibbs measure, and then when you pick 2 guys independently, sometimes they fall into the same pure state and sometimes not. Now perhaps there's one little thing I have to add right now, is that on the toy model, the energies are completely uncorrelated. So the configuration with the maximal energy is really, has nothing to do with anything else. In the true spin glass, there are correlations. So when I say you pick a pure state, it's not exactly a single configuration, but it's like maybe a little bunch of them. So you have to imagine that there's a little grouping of possible configuration that is around something that is good. And there are 15 such groupings somewhere in your sphere or in your space. And this is what the measure for the spin glass wants to look like. Does that make sense? Now, things would be really nice if this were so. Unfortunately, things are more complicated because in the true spin glass models, it can also occur that this sort of splitting gets composed iteratively. So perhaps I should have said also, the toy model, it not only predicts you this sort of, that there will be this organization into approximately 15 things, but in fact, it describes for you exactly the sort of law that these Gibbs weights want to have. It's going to be related to these Poisson point processes that were showing up here. Okay, and this also, in fact, will be preserved in the world of spin glasses. No, it's not just that you have this particular splitting into a few possible states, or maybe little bunches of states, but even the way they spread their probabilities is going to be really the same as that described by this Poisson point process. Now, the complicating factor is that they can do this not just once, but multiple times over. So you have to imagine that, how to describe this? So perhaps one way to picture this thing that I was calling the 15 states is to draw. I'm not sure exactly why I drew it on like a tree for now, but I think that the leaves are my essentially 15 states. And in truth, there's an infinite number of them, but the 15 first states, they capture 90% of the Gibbs measure. The rest is just dust. There are infinitely many, but they are really very small in terms of their Gibbs weight. Okay? So this is how our toy model looks like on this picture. It's just these leaves that have each a particular weight described by a Poisson point process. Okay? But yeah, the extra difficulty is that the true spin glasses can do this iteratively many times. So you should think of this now as being your new blob, and maybe there will be several blobs like this, and each will have a weight described by the same sort of Poisson point process over and over again. Okay, so maybe there is this guy, but it sits next to another guy, which has also its 15 preferred places. And so here that you have a Poisson point process that describes the weights. And first you have to choose which of the big blobs you prefer according to a Poisson point process. And then once you're inside, again, you have to choose which of the final states you prefer down the road. Does that make sense? So it's going to be some sort of hierarchical structure like so. So what do I mean by this? So this is not a picture in real space. It's just a cartoon to try to understand the geometry. And in these dots, I mean little blobs of configurations that essentially are as simple as we can make them be, or in the toy model, it was just a single configuration, and maybe in the true model, it's just a little blur around the preferred configuration. And then what I mean by this drawing is that, so think of this as being represented by a single configuration, even though maybe it's a little blur around a single configuration, each of these leaves. And then the claim that this drawing tries to suggest is that within one of these groups, the distance between any two of these guys will be the same. But then when you go and travel to another group, it will be a different distance. And then the distance between two guys in these two groups will be the same. Does that make sense? So the tree structure makes it natural to represent it, because if you think that these edges have some length, and this has some length, the same length on left and right, and then here the same length on all of these legs, then the distance on the tree reproduces the distance I'm claiming also is going to occur in the spin glass world. Does that make sense? Okay, and okay. Metric spaces that are described like so, like you have this tree, and the points in your space are on the leaves of the tree, and the distance is the way we imagine. They have this property of ultrametricity. If you think about the triangle inequality on this space, it's a stronger inequality than the normal one, because you see that triangles. Okay, so if I try to do a triangle in this space, maybe I take this point, and the point here. I'll have that. So okay, so let me do the triangle. So I have one edge like this to go from here to here. Then I go from here to there, and then from there to there. So you see that the two longest sides of the triangle have the same length, in fact. Okay, and so that's the ultrametricity property. When you draw a triangle, the two, yeah, anyway, okay. I think this is one way to say it, indeed, that whenever you draw a triangle, the two largest sides have equal length. Okay, so maybe I should say the largest is smaller than the maximum between the two other sides. Okay, or maybe I should just say any side of the triangle is smaller than the maximum of the two other sides. Okay, this is the ultrametricity property. Okay, so a lot of intuition that comes here. I'm trying to think how much I can give you some more details. So in practice, if I want to build a toy model for the Gibbs measure, the way I'm going to do it is I'm going to choose these parameters zeta, but I'm going to have not just one of them, but several of them. And then I build, let's say I choose a capital K of them. And in my head, I think that capital K is large. It's going to be the number of iterations of this thing that we do. And then on the first layer, so I have this tree. Maybe I'm going to encode the tree as using this sort of notation, where, so here is going to be, I'm going to define a number u1 associated with this vertex. This is u2. I'm calling this vertex 1, this vertex 2, this vertex 3, etc. And then when I go down there, I'm going to call this vertex 1, 1, and then 1, 2, etc. And I continue down there up to level k. This is u1, 1, u1, 2. Okay, I haven't defined what is u yet, but it's going to be a number associated with this guy. Okay, so for each of these levels, so here I'm going to pick a Poisson point process of intensity zeta 1 over x zeta 1 plus 1 dx. And this point process, it has a finite number of points to the right of 1. Okay, so you can, because if you just compute the integral of that quantity from 1 to infinity is finite, So the number of points that fall to the right of 1 is just a Poisson random variable with a finite mean. So you can order it from the largest value downwards, and I'm going to call this ordering UN. Okay, so U1 is the highest value, U2 is the second highest, etc. Okay, so this is these numbers U1, U2, etc. that I have attached with these guys, and then I continue to do this again and again. So at the second level, I pick, let's say U1n, and then U2n, etc. Independent, and independent from previous things. Poisson point processes of intensity zeta2 over x to the zeta2 plus 1 dx, etc. And I go down my tree like so. Make sense? And then the weights at the very end, I'm going to define them like this. So for every alpha in the leaves, so the leaves are at the last level, at the level capital K, I'm going to set W alpha to be the product along the path that leads to the leaf alpha. Let me write this as U alpha restricted to K, little k, for K between capital 1 and capital K. Okay, remember alpha is I think of it as a sequence of length K of numbers. And when I write like this, I mean you just look at the first little k coordinate. So it will bring you to your ancestor at level little k. Does that make sense? So you do all this product. And these are the weights for your Gibbs measure. This is our toy model for how this should look like. This is a sequence of numbers on the leaves of the tree. It's not yet a probability measure, but you can verify that these numbers, as they are indexed by the leaves, they sum to something finite, so you can just divide by the sum. Let's say proposition. The sum of the W alpha, as alpha is in nk, is finite. So you can set V alpha to be W alpha divided by the sum. Again, I think of alpha as being only a leaf of my tree. Okay? So this defines for me a probability measure, a random probability measure on the leaves of a tree of depth k. Okay? And I want to use this to enhance this external random magnetic field that we were using. Now, so far, we had only this parameter h, and we did not succeed in closing the equation for the free energy. So we want to do something more sophisticated, to have more expressivity in our h, like to bring more power to our to our parameter h. And so instead of this like square root of h z dot sigma, I'm going to try to use that sort of construction on the tree to provide with an external magnetic field that has the ultrametric structure that the Gibbs measure also wants to have, if that makes a little bit of sense. I mean, down the road, ultimately you have to try things and see what works, and I promise that this is going to work.
So
Yes?
in some sense, I allow myself an infinite number of corrections that I can add to my...
Yeah, you can think of it like this. So there's going to be more... Yes?
And then, but at some point, I need to truncate to say, no, I need 15, I need 10, or...
Okay, so yeah, let me try to define my new random magnetic field. So far, I have set up a tree with some weights, and now I want to also have some Gaussians to test against sigma, just like we had just our z before. And these are going to be embedded inside this tree in some sense. So let's say we also give ourselves okay, so first maybe I'm going to introduce parameters. So these parameters are going to, I told you to think about this space as being a metric space with some ultrametric structure, where I did not specify the length of these guys. Okay, so I'm just going to give myself parameters that I'm going to interpret as the length of these edges. These are the QKs. And Z alpha, so these are indexed by all the leaves of the tree, independent standard Gaussian vectors. Okay, and now once I have all this, I can define my new, more sophisticated external field, which is going to be this one. So ZQ of alpha, so I should say for alpha a leaf. I set ZQ of alpha to be something which wants to sum the Z alphas along the path that leads to the leaf alpha. Okay, and also kind of with some parameterization with the QKs inserted so that the lengths kind of match up. Of each of these steps in the sense of the variance of the Gaussian. It's like my analog of square root of 2h, but now I have more freedom to play at each level. And this I multiply by the Gaussian at level k. Okay, so this is my definition for the external field. And now the new definition of the free energy. So let's say for Sk, we're going to set Fn bar of T and Q. Okay, I'm going to say Q is encoding all of the parameters, the Q, the indices here, the Qs, also the zetas. I think of them as being all hidden inside that guy. I'm going to write down later exactly what I mean by Q. Okay, it's not just the sequence of the QKs. Okay, I promise this also makes sense. So now we have the integral over all the sigmas, but also we want to use this new probability weight on the leaves of the tree. So I'm going to write sum over alpha of exponential. So the same thing that we're used to, 2t hn of sigma minus nt, and then plus zq of alpha dot sigma minus again some normalization that just makes me happy, times V alpha, okay, our new probability measure on the leaves, times dPn sigma. Okay, so this is my new definition of the free energy. And it turns out to be convenient to think of this set of parameters as being encoded by a path. Maybe I should have said that earlier. So this again is the Gaussian field. And perhaps the important property to notice is that it has a simple covariance function, which is like 2n. So what occurs when you take two leaves of the tree and you take the covariance between this guy at alpha and this guy at beta? Well, for a while, you will follow the same path on your tree, and so you will get the same Gaussian here. And then at some point, the path will diverge, and then you will see independent Gaussians. So you're going to pick up the variance up until the moment when the paths diverge. So it's going to be Q times the depth of the common ancestor of alpha and beta. Okay, maybe I'm going to write it like this: alpha wedge beta to be like the most recent common ancestor, and absolute value being its depth in the tree. Okay, so that's okay. Just maybe an observation. And yet, the nice way to keep track of all these parameters is to put them all together inside the path. So now when I write this Q guy, I mean the path, which is the following. Okay. So you see that this path contains all the information about the zetas and the q's. It's just one way to keep track of them. And the reason I do it is that if you set the function like this, you can show that that function is Lipschitz in this parameter for the L1 norm on the space of path. So it's very convenient, and also you can interpret the path Q as a sort of cumulative distribution function. Okay, so maybe I'm not going to go into this. All right, so once you have done this, you can try again to calculate derivatives. And I understand that today you're facing a lot of new information on this spin glass if you have never seen it before. You have all these weights, this complicated construction, but calculating the derivative of this thing, in truth, is not too complicated. It's still a sort of Gaussian calculation. You know the covariance according to this formula. You just, decide to not be scared and do your Gaussian integration by parts as usual. So for instance, I could try to see, so if I differentiate with respect to t, as usual, I'm going to get the same expression as I'm used to, the expectation of the square of the overlap. But then I could also try to move one of these qk's around and see what happens. That would be analogous to moving the h around as we had done the calculation earlier, right? Yeah, and notice that now the Gibbs measure that I'm going to write in this expression is no longer just a measure on the sigma. There's also the alpha, which I can think of as being a random variable I can sample according to the Gibbs measure, right? Does it make sense? The bracket of g of sigma alpha is some integral of g of sigma alpha exponential blah, 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 v alpha dpn sigma. So when I differentiate with respect to qk, I'm going to get 1 over n expectation of something that involves both the alpha and the sigma variables. And I get this. Okay, so something that at the same time looks at what alpha is doing. Oh, this I mean the depth. Sorry. Okay, so you can just do the calculation. Okay, now I'd like to, my time is running a bit short. Okay, so just to say this is, a simple calculation. But then I told you it's good to think of this as a function of the path because it has a nice continuity property as a function of this path. And we suspect that the spin glass maybe wants to have k be very, very large. So we don't necessarily want to always keep track of these qk's and move them around. So maybe once you see this, you start to want to switch to thinking about this in terms of this path. What does it mean if I try to think about what it does to differentiate in the sense of the path? Okay, so now I'm going to, instead of differentiating with respect to each single parameter qk, I'm going to try to think that I differentiate in the sense of the path. By this I mean, so new notation, when I would like to, so now I think of, I give myself a function of a path. Maybe I write like this. And by derivative, I mean in the sense that I want an expansion that looks like this, epsilon integral of dqf of tq, of t, yes, q u, q prime of u du, plus little of epsilon. Okay, if you can think that it's just the L2 space with the scalar product, and this is the gradient in this space, okay? So pay attention to the fact, which perhaps is slightly confusing, that I think of the function as being a function of t and q, but then when I write the derivative, it's a function of t and q and the extra parameter, which is varying between 0 and 1. Okay, this is a path between 0 and 1, from 0, 1 to r plus. Yes?
That first term should just be like t, comma.
Yes, thanks a lot. Thanks a lot. Okay, so again, I'm going a bit quickly because my time is running short. But the claim is that once I have this, I'm going to try to move to expressions that just are written in terms of this derivative with respect to the path. And what you find if you do this for the SK model again is you have, let's say, an improved version of this variance error term. Is going to look like that. So in some sense, I want to differentiate with respect to all of these qk's and then square them and then sum over k. And in this like more path notation, this operation will look like this. So dq fn bar squared. Okay, so you should think that this is dq fn bar of t, q, u, which I integrate over u from 0 to 1. Okay, so really think of it as you differentiate with respect to all of the qk's, you square, you sum. Okay, it's just fancy notation to mean the norm squared of the gradient. Okay. So this, what you get if you do this calculation is a sort of conditional variance instead of the standard variance we were having before. Okay, so now instead of being the square of that overlap minus its mean value, is the overlap minus its conditional expectation given the depth of alpha wedge alpha prime. And so then I would need to argue that you should expect this to be small. This is harder to argue, but you want to say that if I reveal to you the intersection between alpha and alpha prime, then you can essentially know what is sigma dot sigma prime, so that this whole thing is small. And so you have to look into this system and argue that this introduces a sort of coupling between the alpha variables and the sigma variables, and you have to argue that the coupling is good, so that if I show you what the alpha variables are doing, you can know what the sigma variables are doing. They want to fall into the same sort of trap. Okay. So in particular, let me see what I want to say. Maybe I'm going to erase because then I can have a bit more space. So yeah, I rushed a little bit through the definition of the free energy, but yeah, it's explained in more details in the notes. And if you were confused, just take it as the message being that when we had only the parameter h, this was not sufficient for us to close the equation, and so we struggled to do something more sophisticated, richer. And we ended up with a function that depends also on the path q. And we suspect that as n goes to infinity, this equation will start to be equal to 0 for reasons not explained, unfortunately. And this is actually valid, so this is a theorem. And yeah, so we proved it with Panchenko, but it's mostly based on earlier arguments. This is for the SK model, which was already understood. And so at the beginning, we just checked that this PDE perspective was consistent with results that were already known. Okay, so this is nice, but just to clarify that it is not a new result in a strong sense. Okay, it's just a reinterpretation, if you like. So it is indeed true that for the SK model, the free energy converges to F, solution to the equation we're guessing. With some initial condition, which, as usual, you can check that the free energy, when you set t equals 0, does not depend on n. Okay, so you still have this sort of one-body property. There's no interaction between the different sigmas. So the function is a bit complicated, But when you set t equals 0, it does not depend on n, as has been the case in earlier models. Okay, and from there, now you know that when we have, this is a Q, yes, when we have an equation like so with a nonlinearity that is convex, we can write a variational representation for this. And from there, and setting Q equals 0 so that all of these extra guys disappear, you end up with a variational expression for the free energy of the vanilla SK model. And you can check it matches the Parisi formula, the one that had been known earlier. Now, what's going on for the bipartite case? Well, you have a guess, which is, it's always the same move. You have your naive equation, which had this product of the derivatives, and then you just replace each of these naive variables, h1, h2, by a path. And you just write down the equation, and you hope this is valid. Okay? If you work through more precise calculations, this is what it does suggest. Is there a question? No, sorry. So let's say, yeah, so unfortunately, this we cannot show, but we can show a bound. So let's say liminf, so for bipartite, the liminf of the free energy is greater than f solution 2 dtf minus integral of dq1f dq2f equals 0. Okay, with again an initial condition that is not too difficult to describe. And yeah, so this is a bit partial, but we can show other things which are, I think, also of interest. For instance, we can show that any subsequential limit of fn bar is going to satisfy this equation almost everywhere. Okay, so I have to tell you what it means almost everywhere in the space of paths, but we can make sense of this, and it's true. But as we have seen, even in 5 dimension, almost everywhere is not sufficient to fully characterize a function. So in particular, in infinite dimension, it's also not sufficient. So we don't know how to conclude. And perhaps the last statement I want to highlight is this result with Hongbin Chen that I mentioned also in the first lecture, which is that we have seen that when we were playing with the variational formulas for the Hamilton-Jacobi equation, we had still this special functional showing up, and I tried to describe a statement with critical points, etc. And this we can justify also in the bipartite or more generally for the general spin glass model that was around. So perhaps I'm already a bit short of time, but let's say a critical point representation. Okay, in my view, so I think it is the last theorem in chapter 6. So if you want to have a look, I recommend. In my opinion, this is the best result we have obtained so far on spin glasses. And as far as I understand, it matches what physicists say. Physicists, as far as I understand, do not say anything more precise than what we have, except that that critical point representation is not a full characterization of the limit, because we do not say which critical point you're supposed to choose in order to give the free energy. We only say the limit free energy is such that there exists a critical point of that functional such that when you plug that critical point into the same functional, you get the correct value. And at small t, there is a unique critical point, so everything's fine. But at large t, there might be several, and nobody has figured out exactly how to describe which critical point to pick. Okay, so just to wrap up, I think even though this characterization is partial, I believe that it can already be used to infer interesting properties about these models, because maybe there are several critical points, but there are not a ton, and maybe they all share the properties that you want to study, and so you can already extract interesting phase diagrams for the model that you care about from this description. Also, if you remember, the way I stated this result in the first lecture was assuming that the limit for energy exists, but in terms of describing the Gibbs measure itself, you can also write things that are only along subsequences. So these are not conditional statements based on unproven assumptions. Yeah, I think I'm already significantly over time. Maybe it compensates for yesterday. Thanks a lot for staying with me, and thanks to everyone.